Sony wanted to keep it proprietary.
Of course they did. But you know, they didn't do that with SDI, and it changed the world.
And it also put them in a spiral.
In a bad way or a good way? You mean in 1991, 92?
No, I mean, SDI has been kind of the downfall of Sony in many ways, and what I saw the 14 years I was there, because it became such a universal tool that everybody, and even consumer, started using.
Okay, folks, take a seat. Grab any more food you want to do, and let's get going. Okay. Well, welcome to the last meeting of the session for this year, the centennial year for SMPTE, and we had some great celebrations. I hope you've had an opportunity to take some of those in with you. And tonight we have Al Kovalick, who's a great supporter of the section here in the Bay Area. He's going to talk about the future of the media industry, and like way deep into the future. So he's got the DeLorean parked outside, and we're well ready for that.
And the flux capacitor.
Yep. And
How much buffer does that?
so this is sort of an extension of the talk that Al gave at the in Hollywood earlier this year. So hopefully we're all ready for that. So Al.
Okay, thank you, Keith. Let me put this down, and I welcome questions along the way. I know probably half of you here. I'm a local guy, and thanks to Pradeep for opening up Cisco for this, and we all appreciate that. So yeah, I did give a talk somewhat similar to this at the SMPTE conference down in LA, but most of you probably weren't there. Only two people that maybe, I don't know if John, were you in that session? And Ed, you were there? Pradeep was in my session actually and gave a talk of his own with Shubha Desikan. So I because of the 100th anniversary of SMPTE in 1916 with Charles Francis Jenkins, I thought I would look ahead a little bit, and I didn't know how far. So I put this title on the first page, and I had no idea what the content would be. But I thought, I'm going to have to research this and hopefully come up with something that's in fact believable. And I think you will find it believable. I wrote a paper on this as well. It's 15 pages. It's not a part of this, but it's a paper that I wrote that's in association with the formal presentation that I gave at SMPTE. And if you want a copy of that, I can probably give it to you. So it tries to look ahead, not 100 years, because that would be ridiculous. It tries to look ahead 20 years. And I picked 20 years because it's actually believable. And I think I can prove this to you as we undergo this presentation. I'm probably out of the frame here. Tell me where I can walk before I'm too far out of the frame. I probably already am. Can I get over to here? That's good. Yeah, okay. Because I'm also going to have to advance the slides. So what would the media enterprise look like in 2036? I'm not trying to tell you what the content's going to be or what the distribution mechanisms will be. ATSC 4.0? I don't know what it'll be called by then. How much of it will be over OTT? I don't know. I'm not making those predictions. But with regard to infrastructure, how you build systems, that always interests me. So is it a fool's errand to look ahead that far? You know, we could have an earthquake here in 10 seconds, heaven forbid, and I couldn't predict it. But I'm telling you, we can look ahead 20 years with some level of confidence. Okay? Let's see why. First aspect here is accelerating technologies. There's a little short review of that. And also the second part will be the evolution of infrastructure. So we're going to break it into two pieces. Now, maybe you've read this before. Prediction is very difficult, especially if it's about the future. I've certainly heard of it before. But usually I think of a baseball player. A famous baseball player has this quote. Who would that be?
Yogi Berra.
Yogi Berra. Right? Well, Yogi Berra, he may have thought this up by himself, but most likely he heard it as a Danish proverb and maybe just reiterated it, and it became his. Actually, many people have said this quote for the first time, if you look into it. But Niels Bohr was a physicist. He was a quantum physicist. And he probably was quoting a Danish proverb from his own country. Now, quantum physics is amazing.
Actually, we do need to have the light on. Sorry.
If it's getting dark up in Sacramento, because we shut the lights off in the room here a little bit. Hold on for a second. Niels Bohr was the first person to say, he said, if you think you understand quantum physics, you don't understand it then. By definition, you don't understand it. I want to talk a little bit more about that later on, actually, because that's part of our looking ahead 20 years. But Niels Bohr also said this. I love this quote. Technology has advanced more in the last 30 years than the previous 2,000. The exponential increase in advancement will only continue. Now, he may have said that in 1960. That means he was thinking between 1930 and 1960, he saw an exponential advance in technology. Now, from our perspective in 2016, that's probably a joke. It was minor. Right? It was major in a relative sense. Go over some examples. But here's the point. That this is just as true today, and we know that it is, as it was back in Niels Bohr's day. So I'm going to take that first quote and modify it based on his second quote. Prediction is not very difficult, especially if it's about the future of technology. And again, we can't predict an earthquake, but we can actually predict with a lot of accuracy what will happen next year with regard to certain specifications of products that you can buy off the shelf. Now, I read a book by David McCullough. It's a wonderful book on the Wright brothers. I highly recommend it. He's a great and entertaining writer, of course. And he really instilled within me beauty of what Orville and Wilbur did with regard to building the plane, how difficult it was, and how analytical they were in building wind tunnels in the back of their bicycle shop, and having to transport this 450 miles to Kitty Hawk that had just the right winds. It's a beautiful story. And the very first flight, this is Orville Wright, and who do you think this would be? That would be Wilbur. And they had a neighbor, even though this was like a sand dune of a little island, North Carolina, they had a neighbor they invited to say, please take a picture if you see something interesting. They like to document what they did. Well, that was only 12 seconds in 1903, the very first flight. And of course, it kept increasing in length after that. Charles Lindbergh's New York to Paris trip was 3,500 miles, and that took him about 33 hours in 1927. So in 24 years, there have been 17 doublings of flight. It's about 1.5 times miles per year. So if it was 3 miles 1 year, the next year it would be about 4.5 miles, or 1.5 times approximately. So you might say that's kind of like what famous law of electronics? Moore's law. Except that we can call that Wright's law. And a lot of things actually have Wright's law-like characteristics. So let's look at Moore's law. We're in Silicon Valley. It's a beautiful place because this is where the law was invented, not too far from here. I think Moore probably sat on the corner of of Central Expressway and Bowers, because there was an initial Intel plant there, and I think that's where Intel was founded, on that corner. And he may have sat in one of those offices when he penned this. So in 1965, in the Electronics magazine, they don't exist anymore, but that was the magazine back then, he did this graph here where he plotted on the x-axis the date, and he found that this is a log base 2. So he said in 1961, there's going to be 8 transistors on a chip. And in 1964, there's going to be 64 transistors on a chip, 2 to the 6th, and so on. And he plotted it out to 2 to the 16th, which is 65,000 transistors. Now, he didn't know what was going to happen, basically, 10 years later, but all good engineers extrapolate. That's why they're engineers. They look, what could it be if I drew a line? So he drew a line out to here. Could he have imagined that it would get to 2 to the 35th transistors in 2016? Now, the Intel Altera Stratix 10 FPGA has 30 billion transistors. Pretty close to 2 to the 35th, actually. So Brian Krasnich, the CEO of Intel, said our current Moore's Law cadence, it's not 1-to-1 the way it was here. It's closer to a doubling every 2.5 years. So this law has done things that nobody could imagine, because people can't imagine exponential growth. It's just very, very difficult to do that. Even Gordon Moore couldn't possibly have believed that this would have been the case. Here's a simple case where the very first IC, Jack Kilby, still alive, got the Nobel Prize for this in 1958. It was a phase shift oscillator, had one transistor, a couple of resistors with an external capacitor, and a sine wave coming out. And Gordon Moore knew about that, and he put that down on his chart as being basically 2 to the 0, one transistor. That was the very first one, and then it built from there. This isn't the largest chip. It only has 2.3 billion transistors. This is a 8-core Xeon CPU, and that was from 2 years ago. Now, disruptive technology. I think we'd all have to admit that newspapers have been disrupted. Many of us maybe read the Mercury News here in our area, and like a lot of newspapers, they're trying to reinvent themselves, and they're struggling to deal with this other disruptive technology here. So here everybody is waiting for a ride, and they're reading the newspaper. Here they're waiting for a ride, but they're looking at their phone or their iPad. I think that's a telling story that not only is it disruptive for that business, but there's a parallel, there's an analogy of how it's disruptive for our business. I'll give you some examples of this disruptive technologies. Scribes in the book, arrows and guns, horses and cars, telegraph and telephone. You've all heard of the company AT&T. What does AT&T stand for? What does it stand for?
American Telephone and Telegraph.
No, it doesn't. It used to stand for that. Now it just stands for AT&T. That's same with BT. British Telephone only stands for BT. It's a sound. It doesn't have any meaning. Why? Because they dropped the meaning, because it's meaningless. Because they're not in that business anymore. But the fact of the matter is, they did a pretty good job of going from telegraph to telephones. You'd have to admit that. They sort of invented the modern telephone system. They had a monopoly on it for a long time, almost throughout the world. But they reinvented themselves. People that made vinyl still popular to a certain niche of people, but vinyl and CD have been replaced by Pandora to an extent. And point-to-point internet, pre-web and web. And I thought about this when I was writing this paper. What came before the web? Well, the only thing I can think of is a library with a very fast courier. You know, that would be about the only thing you could come up with that would be even close to the instant access. But even that probably wasn't practical, as they didn't have very fast couriers. I think Sony knows something about the demise of CRTs and the takeover of LCDs, DVD, Netflix, maybe videotape. Yeah, that's something we know about, and servers. Now, I worked on helping to put videotape to bed when I was at HP, working on file-based workflows. Everything was disk-based and IP-based, and that was in 1991 here when I worked at HP, Cupertino. Now, and these are in red because they're right now affecting us in this business. One is custom AV, which many of us in this room have built custom AV products, is now IP-based, Ethernet-based, and COTS-based, commercial off-the-shelf. And facility-only based systems are transitioning to cloud-based systems. Now, this is a work in progress. This isn't done yet. But these same transitions that have occurred are also occurring for our business right here. So let's talk about linear versus exponential. If I take a step and it's 2.5 feet, then after 30 feet, I've gone 30 human steps. I've gone about 75 feet. That's easy for anybody to understand. 75 feet. What if I took, though, an exponential step? So the first step is 2.5 feet, and the second step is 5 feet. Now, I got to have some pretty long legs to demonstrate this. And the third step is 10 feet, right? Because I'm going from 5 to 10. I'm doubling it every time. How far do you think I would get in 30 steps? Any guesses? 100 miles? 10,000 miles. What do you think? 10,000? Yeah, 100,000 miles. Who says 100,000 miles? You're not even close. It's 1,000,000 miles, and almost exactly 1,000,000 miles. 1,000,001 miles is the cumulative distance you would have walked with just taking 30 steps, as long as each one doubles. So this is the magic, you might say, of the exponential function. And many things in our business, and I'll talk about the different generations of change that have all been on exponential growth periods, have exponential growth. Many of the examples in the previous slide had exponential growth periods. Almost all of them did. But nothing lasts forever. And many growths have a slow start, an exponential period, then they peter out. Either they come to a complete stop, like buggy whips, and to a certain extent slide rules. I guess you can find them, but they're certainly not a growing business. But all these examples up here sort of came to a dead end or have plateaued. Now, it's not all growth continues. And some people say, faith no more. By 2025, maybe Moore's law will in fact die. There's an excellent article in Economist magazine. I think it was probably about 4 or 5 months ago. And they had a great analysis or study of when is Moore's law coming to an end. This has been discussed many times, of course, over the last 57 years since Gordon Moore penned that article in Electronics magazine. But some people feel that you're not going to get much farther than 2025. And there's a lot of reasons for it. But one reason is that the cost of a 5 nanometer transistor chip, a fab that has that kind of resolution, will be $16 billion. Now, that's a lot of money to spend for a fab. Anybody here have that kind of spare change? I mean, we'll check your wallet later on. That kind of money tells people that we're going in the wrong direction. You know, we've seen the end of Moore's law. As I say, faith no more. I read a fascinating article by a scientist who predicted the end of Moore's law by 2600. And of course, that's so far out. But it had to do with a theoretical computer that was built, and you couldn't have any more transistors than it would sort of fit into the universe because it was growing so rapidly, because as we know, things grow exponentially very fast. But there's an interesting picture here, and there's a bit of an S here. You can see that? So this is the traditional S curve when something has a slow start, an exponential midlife, and then it has a point where it actually dies. And all those previous examples I gave, they were S curves. Interesting thing about S curves is, Gary, is that one S curve usually replaces another. And you can see that in many different aspects of technology. I'll give some examples of that. Oh, but first, anybody know what Moore's law is? Pradeep probably knows. The number of people predicting the end of Moore's law doubles every 2 years. Now, there's 7.5 billion people on Earth. So at some point, everybody on Earth is going to predict the end of Moore's law. There's nobody left to do any work. They're just predicting the end of something, so probably it would end. Well, you could have said that 10 years after Moore's law started, or 20 years after, or 30 years after, or 40 years after, or 50 years after, or 60 years after. You'd have been wrong. So at what point will it actually completely die? I don't know. Here's something that I'm pretty certain of, and this is just the believer in me. The most fundamental thing in digital electronics is what? The binary switch. There's nothing more fundamental than that. And we use the transistor to do that switching function. Does anybody really believe that the binary switch, somehow scientists will say, I've given up trying to improve upon it? I don't think so. I think we're always going to be working on a new version of the binary switch. It may not even be called the transistor, and it may be Moore's law 2.0, but we're going to continue along this path for greater and greater density. Maybe three-dimensional circuits, which already exist to a certain extent. Well, we'll see. So let's talk about now how we apply these S curves to an overall exponential growth over a long period of time. Here's an example here of quality. I call it progress or quality. This is the quality of, let's say, a video signal. And this is time. So this goes back to Charles Francis Jenkins in 1926 when he had his radio visor. And John Logie Baird when he came out about a year earlier and got the public demonstration of his model of a television in the UK. And this continues along with very simple technology over here, but over time it grows and grows and grows, and I'll give some examples. Now, I give an example here where image quality doubles about every 4 years, or since about 1941, let me think now, since about 1951, which is sort of the color range, up until today, image quality has improved about 80,000 to 1. Now, you could argue that that number's wrong because image quality is in the eye of the beholder. I'm just looking at the metrics of frame rate, of bit resolution, of color abilities, contrast ratios, those kinds. If you factor that in and you go all the way back to mechanical television, you get about 80,000 to 1 improvement over time. And each of these, black and white S-curve, color S-curve, of course there's still color today, but it's being improved upon. The HD S-curve. Yes, HD will, quote, die off because being replaced with HDR, wide color gamut, high frame rate, up to 8K pixels. Someday this will look like a joke. 8K, who could live with that? For whatever reason, your whole wall, your whole house is a television monitor. I don't know. There's been a lot of thought about why you'd need more than 8K. And then eventually, something else, but I don't know what. Now, actually, this number 80,000 I think is wrong. It's probably more like 1 million or probably more. Why? Let's go back to 1878. Keith, what happened in 1878? Willoughby Smith, he was a telegraph engineer, because everything started with the telegraph after all. That was the first communication mechanism, really, that used wire and electronics. He discovered that selenium was photoconductive. Now, photoconductive is not the same as photoelectric. Photoelectric is like a photocell on the roof of your house. It generates electricity. Photoconductive, you're just modulating the resistance of a device. He saw that, and he started to think and dream it was possible to move an image from one side of the desk to the other over some wire. 2 years later, 2 professors in England actually devised a system. It's so impressive. They used a mosaic of selenium cells, think CMOS image sensor. They used a wire for each of the elements, a wire, each one had a wire, over to a micromirror, think TI micromirror display, and they actually proposed that to be a working television system. They couldn't build it for a lot of reasons, but they're only ahead of their thinking by about 100 years, because in the 80s that kind of concept became much more popular with CMOS sensors. So if you start with 1878 and you go way back to here, the first thoughts of an image, up to where we are now, the quality has probably improved by at least 1 million to 1. So you see the importance of the S-curves. One follows another, and that's a key in understanding how things move forward. So let's look at now the evolution of infrastructure. We want to look at storage systems performance. What could it look like in 20 years? Compute systems, network systems, and eventually we'll look at infrastructure, which is a combination of all of them, and what they could look like in 20 years. So let's predict hard disk storage capacity. Now, this isn't magic. I'm applying Moore's law kind of thinking, because Moore's law has applied to hard disks as well as ICs. You don't count the number of transistors, but you really count the bit density of how much a surface per square centimeter could store, say, in a magnetic sense. So from 1956 to 2014, magnetic drives have followed Moore's law with a cumulative annual growth rate of 41% a year. So it's very impressive that actually they're sort of tracking one another. Of course, some of the techniques are similar. They're using photolithography to do certain things, and what helps one helps the other. And if we look at a conservative rate of a doubling every 3 years, and that's conservative because it's been 41% a year, we bring it down to 26% a year. Then you can look at this graph here that goes from 2016 today with a 4 terabyte drive, although you can buy 8 terabyte drives, but 4 is sort of a common one. And in 2037, you'd have a 512 terabyte drive. Now, if you sit there and you say to yourself, Al, it's never going to happen, you're nuts. And I'm saying you don't believe in the exponential function. And you would deny Moore's law could get to 2 to the 35th transistors. Yes, it'll eventually come to an end, but it may get to 512 terabytes on a platter. And there's work going on, as a matter of fact. I don't think it says so here, or does it? No. There's work going on by some researchers in the Netherlands at 500 terabit per square inch storage mechanisms. So maybe it'll be atomic storage, it may not be magnetic, I don't know what it'll be, but I don't think we're going to stop looking for ways to get more and more density. So that's storage. Now here's one more aspect of storage. I'm only going to have 1 or 2 examples for each. How many of you know about the Powderhorn system? I worked on that thing. You could live in there if you were homeless. You could actually drive in a small car, and you could live in that thing. And if all the tapes were nothing but videos, you could keep yourself entertained, I guess, as well. So that was a 10 terabyte unit in 1998, 10 terabytes. And in 18 years, there's been a 3,700 to 1 improvement in density. Linear tape opened the LTO drive today with basically 1.6 carts. So 1 full cart and 0.6 of another is equivalent to 10 terabytes. So I think it's impressive that whole live-in mechanism is reduced to just 2 tapes you can hold in your hand. Now, we can say the same thing, but what about the future? Let's look ahead. Now, I'm not going to go ahead to 3750. This gets into why is that such a big number? Well, there's a lot of reasons for it. It had to do with the relatively small tape drive capacity of 1.6 gigabytes per cart. But if we look ahead and apply some Moore's law to it, we're going to have 1 petabyte per device. It may be tape based. It may be optical based. It may be who knows what based. But it'll be possible, not impossible, to have 1 petabytes per device in 2036. And if you say that, Al, you're nuts, that's not going to happen, what don't you believe in? The exponential function. And you think that Moore's law, or something like Moore's law in this case, is dead wrong. Maybe it is. Maybe it will peter out. But something's going to replace it. That you can be sure of. So this is just the case of magnetic storage. Let's look at the CPU. So we're talking about 3 things. Start with storage, CPU, and then we'll look at networking. Here's the case of the Xeon Broadwell processor. It's got 24 cores. Only 22 of them are being used. Do you know why? Yield, right? They take the 22 that work out of 24. Because frankly, when you build something this big with so many billions of transistors, you only have to have 1 bad transistor in some cases, and it's not a functional core. So that's a mechanism or a strategy to be able to save, and that's been going on for a long time, that particular method. But if you apply Moore's law to this in 21 years, you'd have 3,000 cores and about 9 billion transistors. And if you believe that's not going to happen, what don't you believe in? The exponential function. You think it's phony. If you tell Gordon Moore that. Fortunately, he's still alive. Now, this isn't to scale, and will it actually be 3,000 cores? I don't know. But even if I'm off by a factor of 2, I'm only off by about 15%, just to let you know, because it's exponential thinking, not linear thinking. Now, this is not quite a Moore's law example, but I think it's an interesting one. So Google has invented this thing called the Tensor Processing Unit, TPU, and they have their own chip, ASIC, that they've developed for it. And it delivers an order of magnitude higher performance per watt than any other commercially available GPU or even FPGA. And TensorFlow is an open source software library that runs on this. So when you speak into an Android phone and you use the Google Assistant, there's a very good chance that your request is going through something like this in order to be processed. Many people believe this is the next wave. Beyond compute, it's artificial intelligence. And it's units like this that in fact may be following Moore's law in terms of transistor density, have broken away from Moore's law in this important way that performance per watt being 10 times better than a regular GPU or an FPGA is impressive. So it was shifting the domain a little bit as to what the important metric is, but in terms of AI, that's a very important metric. So in researching this, I wanted to figure out, see if anybody has done research to say, when will machines be as smart as humans? That's the ultimate question, right? Alan Turing. I just got back actually from a trip to London. I went there on a business trip. And I went to the Bletchley Park. You've probably been there. Have anybody been to Bletchley Park? What happened to Bletchley Park, Keith?
The headquarters of the code breakers from
Yeah.
Enigma and Colossus.
Right. So you can go there and see the machines that were built, that were designed, well, were conceived by Alan Turing to hope to actually were used to code break the Enigma. And the Colossus was to code break the Lorentz encoder, which is actually a computer. But he started the idea of artificial intelligence by saying, I'm going to ask questions of a machine, and if I can't tell it's a machine or a human, then you pass the Turing test. I'm oversimplifying it, but that's basically what he said. So here's these two professors from Oxford University, and they found the end of the report was the results reveal among 550 experts, so it took them a while to compile this, that AI systems will probably, 50% of them, 275 people, said that they would reach overall human ability mentally. I don't know about conscience. There may not be, or being aware in that sense. We'll see. But in terms of problem-solving ability, by basically 2040 to 2050, but very likely with 90% probability by 2075. Now we can say this is, who cares? They're looking out so far, they're all wrong. But I think it's interesting that 550 experts sort of have this feeling. They see the current growth rate of AI and how impressive it is. You take out your phone and you speak to it, and even in a noisy environment, it pretty much knows what you're talking about. Any of you have the Echo, Amazon Alexa? Yeah, I'm not working for Amazon, but I love that thing. I have it in my kitchen, and frankly, it's very functional. And it answers pretty simple questions accurately. And if you have one, just to see how smart it is, ask it who's buried in Grant's tomb. You'd be surprised. I'll bet you don't know, and it does. So that'll give you some ideas as to what's possible with artificial intelligence. Now, why do I bring up artificial intelligence? Because it's going to be a key to running our facilities in the future. And if you think not, I think you're wrong. Because it's growing at an exponential rate itself. The number of companies and startups, the number of available APIs that are in this space are growing exponentially. The other day I was experimenting with IBM Watson's API. You can, any of us here in the room, get access to it at the demo level. Plus you can just pay for it if you want to. It's only so many dollars per 1,000 calls to their API. But I was experimenting with speech synthesis and creating expressive speech. And using Watson in real time, it's very impressive. And I can imagine companies at this table that want to use that for their own products, for whatever reason. There's just so much richness here going on, and to be a part of it is very exciting. Let's look now at networking. We looked at storage, we looked at CPU, let's look at networking. Now, this is from the Ethernet Alliance, and you might not be able to see the whole slide, all of the detail on the video here. If you want to switch to the slide, Keith, that would be good. But we're seeing here before 2020, we're going to have 400 gigabit Ethernet. Right now, 100 gigabit Ethernet is relatively common. 40G is common. 25G is, I don't think it's quite a standard yet. Is it, Pradeep? But it will be? It's shipping. It's being shipped, but I'm not sure if it's gone through the final IEEE specs. But it's been shipped for over a year. There'll be 50G as well. There'll be some lower speed versions. But they even predict that before 2030, they'll have 6 terabit per second Ethernet. I couldn't have predicted that. Actually, I could have predicted that, actually. John's phone would go off. And why would you need 6 terabit a second Ethernet? You going to plug that into your laptop? Well, you might.
For all the 8K screens that are out.
For all the 8K screens. Well, actually, Keith was just telling me, and I couldn't make that one, but the Litro cinema camera some of you might have gone to see that. I don't think you can buy it. You have to lease it. I mean, it's a monster, right? It's a huge device.
You called it a big girl. The big girl.
We look at it now. We look at it. We look at it now, and I'm sure looking at it in the future, it's going to look like, wow, it was that big. Like the first Ampex VTRs were basically two washing machines side by side, right? Now that device, uncompressed, it has a compressed output, of course. But if you look at the uncompressed output, there isn't one, but if there was, and they could certainly do that, at least in the lab, it's about 2.7 terabits per second. Raw, native, Lytro cinema camera output. Call it 3 terabits a second. If you had 10 cameras of that on a venue, a sports venue, and you wanted to produce, you'd need 30 terabit a second switching fabric. Today. Do you think we can use a 6 terabit link before 2030? I think we can. Probably if they had one, Lytro would use it today, as a matter of fact. So now Moore's law, it's following Moore's law. It has nothing to do with Moore's law. Why? Because Ethernet speeds have nothing to do with transistor density. It has to do with transistor speeds, that's true, but Moore's law doesn't say anything about speeds. It says the devices per chip. That's what Moore's law is specifically about. So it's following Moore's law in that it's been on exponential growth since it started back in the early 80s, when it was only about 2 or so megabits per second. So let's talk about switch and router performance. So you can get a switch today, a standalone 32-port, 1 rack unit high switch with 40 G ports, and that's equivalent to about 1,700 SDI ports. Now, the beautiful thing about Ethernet is that it's bidirectional, whereas SDI is not. And you can put multiple signals on an Ethernet cable, which you can't do that with SDI. You've got one SDI signal, that's it. So you get an interesting packing advantage when you use Ethernet and IP. So let's say this switch will be used in a video over IP network. Well, here's the 4 different dimensions that we care about that have growth. The first growth path, and this kind of follows Moore's law, although it has to do with speed and not density, is that the ports started off with small 10 megabit ports, and now you can get them with 100 gigabit ports, and in the future 400, and maybe in 20 years 6 terabit ports. So that's going to follow a Moore's law kind of thinking. And then finally you have, well, not finally, but the second point is routing performance. Now that is following Moore's law. Specifically, why? Because the switches themselves, and we're in the house of switches here at Cisco, the switches themselves are built out of silicon. And the packet inspection and the packet routing and the fabrics are all silicon based. So as silicon goes, so goes switching performance. There's no doubt about it. And it's been that way since the very beginning, from the very first switch that was built. So we're depending upon this to be able to have better routing performance. And one of the things that I like is the fact that, and routers to come, I mean, you can look in at there's a protocol that's being used. If you're not familiar with it, you'll hear more about it because it's part of the work that SMPTE is doing to package video over IP. And in the RTP protocol, there's a bit called the M bit that basically says this is the end of the video frame. And it would be interesting if a router would look at that M bit. It has to drill down through deep packet inspection, say, oh, this is the end of a video frame, time to do a switch. Now actually Cisco, 2 years ago at NAB, showed a demo with an off-the-shelf switch showing frame-accurate switching. In that particular case, they were switching during the VBI, but it was a very impressive demo, and it showed the world that you could take a switch and cause it to switch during the VBI. Now, that wasn't necessarily something that Cisco wanted to productize, but it was a demonstration to show that, first of all, Cisco is very involved and deeply cares about this industry, and that also, yeah, an off-the-shelf switch could actually do it. So it's only going to get better. When people say it can't be done, I always say, yes, it can be done. You just don't understand it. The next aspect is scale. You can have all the switches you want, but they can only get so big. And at some point, you want to scale them. And the leaf spine architecture, and I won't get into the details of it, but basically it's a 2-layer architecture, 3 hops between switches, scales beautifully. And you can have hundreds of thousands of equivalent SDI links passing through this. And you can have 2 of them in such a way that if one dies or if one path dies, another one can take over for full redundancy. It's as bulletproof as you'll be able to get. And so that's a way to scale to 16 times what a switch can do, or much, much more. And finally, one of my favorite topics is software-defined networking, SDN. And that's the control aspect of it. You can look at that and say it's got nothing to do with Moore's law, but it has a lot to do with software. And infrastructure systems are composed of software-defined networks, certainly a software-defined compute, which is virtualization and containers, and software-defined storage. And in the SMPTE journal, I guess you're all SMPTE members. If you're not, I'm going to shame you, but you probably are, especially on the 100th anniversary, right? We need to be SMPTE members. The journal that came out in about August, which is the 100th anniversary journal article, I put an article in there on software-defined systems, describing software-defined networks, compute, and storage. And SDN has an advantage in routing video over IP because it's very deterministic. And when you go to NAB and IBC and you go to a vendor's booth and you ask them, how do you route your signals from input to output to guarantee quality of service, no packets dropped, very low latency, very low jitter? They'll tell you, well, yeah, we're actually using SDN techniques, and this is the way that we're doing it. Very few people are relying upon off-the-shelf protocols to do the routing for them because you don't get the quality of service that you want. All right, we talked about these important points of storage, compute, networking. Let's look at the infrastructure itself. There's only a few more slides here. I want to apply the S-curve again, this time not to individual technologies, but to an entire infrastructure. And let's see how this pans out. What we want to look at is basically the progress of quality, of workflows, of connectivity, even of Moore's law, in an infrastructure sense over time. This will be revealed here. So we're going to start with, I'm not even going to go back to mechanical. If you go back to mechanical, you're talking about 30 lines of video, 15 frames a second. And it wasn't even black and white. It was orange and less orange. And do you know why it was orange and less orange? Because, well, but not really phosphor, but well, in a way, yes, and I'll tell you. Neon, but why neon?
Because you can switch them all off.
Exactly, because incandescents have a dwell time, right? You heat up an incandescent, it's not going to cool off fast enough for the next pixel time. So they used neon bulbs they tend to be orange. So yeah, you looked at anybody on these early displays, they're pretty ugly because they're orange or less orange. So if we went all the way back there, we would certainly talk about that. But we've had about 11 stages of infrastructure advantage, or I should say that they've been increasing in advantage through 11 stages since, well, about the 1920s, I guess we could say, is where it started. We went from analog to digital. And when I say digital, I'm not talking about Ethernet. I'm talking about what? SDI, exactly. Keith says SDI. Video people say that digital is SDI. Now, people outside this world don't necessarily think of it that way. They say, isn't Ethernet digital? Of course it is. But it's not a generation that we call digital. We tend to call it SDI. And I'm saying we're in this range. Well, this is 2016. So we're here. It's starting to peter out because it's being replaced with video over IP. So in an infrastructure sense, we have a lot more commercial off-the-shelf systems with IP moving AV. Now, back in the 1990s, actually, when I worked at HP and we built a video-on-demand server, and we had 1 gigabyte hard disks, I thought I'd died and gone to heaven. I didn't appreciate Moore's law. That would be 8,000 times better than that just since 1991. But we were moving files using TCP and FTP, and we didn't have videotape for any of this thing in 1991. And it was the very, very beginning of file-based workflows. And many stations, if you walk into Discovery, for example, which I have many times, it's hard you won't even see an SDI router except in a couple of places. They are a file-based workflow plant by and large. I'm not talking about the final distribution to the air. Some of that's, of course, real time. But 99% of what they do in their facility is file-based workflows. So file-based workflows have had a huge impact. And I suspect there's not a single designer here that would say they would rather stream something live than use a file. The file is just a better way to do it, if you can do it. But you can't do everything with a file, especially live sports and live events. So many things are with COTS and IP, but still we have SDI, so they're existing contemporaneously right here. Well, what's next in terms of infrastructure? Well, software-defined media infrastructures, and I mentioned that software-defined storage, software-defined networking, software-defined compute. And that includes private and hybrid clouds. I'll talk about the cloud in the next slide. But there is a big change in our industry right now going on with regard to the acceptance of the public cloud. I gave a talk at SMPTE 5 years ago down in Hollywood, and I thought I was going to get thrown off the stage because I talked about the cloud as a place where we could run our station infrastructure. Nobody agreed with me. Well, frankly, I didn't agree with myself because it was a bit early to actually do that, but it wasn't too early to start thinking about it. There's a difference. So this is starting to catch on in a major way. You can find systems built today, and I know them because I work with some of these companies as a consultant, that have built 100-channel linear systems all in a private cloud. Now, as soon as they open it up for the public to use, it becomes a public cloud. It may not be Amazon, it may not be Google or Microsoft Azure, but it's still public in the sense that it's being shared by multiple customers on the same infrastructure. So this is a very, very hot area right now, and vendors that understand where this is going are taking advantage of these kinds of systems, and they're building their products to run in the cloud, pure and simple. And if they don't, they'll be under a dark cloud. What comes next? Really, full public cloud for everything that's being done. Now, you can probably say, what if I'm doing the Olympics? Am I going to use the Amazon cloud for that? Maybe not every corner case will be used in the public cloud, but many things will. Anybody know what SaaS stands for? Software as a service. So basically that's, instead of an installed app on your computer, you're running a web app. And you're running the execution engine somewhere in the cloud. I have several apps that I use. I have an accounting one. I have one for keeping track of my time and my clients. It's called Paymo, and it's $20 a month. Here I'm doing an ad for it, I guess, because wherever I log on in the world, if I'm traveling, no matter where I am on my phone, on my laptop, on my tablet, I've got access to my accounts. I can add expenses. And what I love about it is about every week, sometimes I just leave the thing on, and a pop-up will say, there's a new version. Yes. 2 seconds, I got a new version. I mean, how can you beat that? You can't. I love that. Who here loves installing software on their PC? Please raise your hand, right? You just won't get a hand to go up. I mean, installed software sucks. Now, there's a place for it. I get it. There's still a place for it. Really high-end, color correction, 8K stuff. Yeah, I'm not going to run that in the cloud. I might run it on a private server right here and run it still in a browser. And companies who don't make those kinds of products are looking for trouble. Now, Sony has a thing called the C-Suite, CI, and there's 4 or 5 SaaS apps that you can subscribe to and use. A lot of it's used for theatrical work. But many companies are looking in this area, and they realize that that's the game of the future. Now, the next one is XaaS. Anybody knows what that stands for? Because that stands for everything else. It's anything as a service. Now, I mean anything as a service, I mean anything as a service. You can go to, again, I use Watson as an example. They have about maybe 10 different domains that they're looking at, all as a service, including artificial intelligence as a service. Just tap into the API and use it. And frankly, it's not that hard to use. Now, I'm not an expert in that area. The fact that I can use it and get results impresses me. I'm not that smart in that area. But it shows that we all have access. Our engineers can get access and start to learn and try and experiment with things. You want disaster recovery as a service? You got it. Storage as a service? You got it. Play out as a service? You can buy it. Asset management as a service? You can rent it. Amazon Marketplace. You go into the Amazon Marketplace and just look at what media applications are available that you can run yourself as a service by the hour. I love the fact that the cloud is sold by the hour. Now, I have a phone here. I did a test on this thing. It's AT&T, and I shut it off for a month. And I had the switch off, so there was no power going to it whatsoever. You know what really disappointed me? AT&T still sent me a bill for $150. See, that doesn't happen with Amazon. When you say, shut my instance off, they charge you what? Nothing. Not even a little bit of keeper you'll lose unless you pay 50 cents. You're not going to be able to keep it stored in the system. But that's fair. If you take it off the system, they charge you nothing, and you just can reload it again. This year, I think, marks a turning point where the clouds, well, I'll talk about that actually in the next slide. And what comes after this? Quantum computing. In 2017, Chinese and the Austrians are going to launch a satellite called the Quantum Science Satellite. This is a fact. And what they're doing, if you know anything about quantum entanglement, it's a way to transmit information using entangled photons. You could use other particles as well, but photons seem to be easier to work with. So you can imagine on Earth I have two photons that are cousins, and they're aligned. I'm going to put some of, let's say I have these photons here that are aligned with these photons. I'm going to put these 5 in the satellite and put it in a little jar and keep them stable. Now they're circling the Earth in a low Earth orbit, but they're certainly a long distance away from the 5 that are on the ground. Now, the cool thing about quantum entanglement is they call it spooky action at a distance. So if I've got the satellite up here, and this will happen next year, and I have these photons here, if I change the state of these photons and change the spin from up to down, what happens to these? They all go down instantly. And if you think you understand that, see Niels Bohr, because he says you don't. It doesn't happen at the speed of light. It happens instantly. The point is they're going to be running experiments to show how files could be transferred from here to somewhere else without electromagnetic radiation, and not using a laser beam, not using a fiber, but using spooky action at a distance. Will that happen someday? Will Keith be sending files from here and to the UK using quantum entanglement? Maybe so. We'll see. It's very exciting, I think, what we have in the future. So right now we have all these happening at once. I'm not going to say this is happening with regard to quantum entanglement, at least not in our business, but we have 4 or so simultaneous S-curves occurring in 2016. And as this moves to the right, some will drop off and some will get stronger. So this is the last slide. Don't bet against the public cloud. So here's what's changed this year, is that the trust is more important than security. The trust in the public cloud vendors, especially Amazon, Azure, Google, and IBM, has changed dramatically. And one of the reasons that there's so much trust now is, what do you think? They're making money. Amazon has proved, they're a $12 billion run rate right now, and they're profitable. Jeff Bezos said that he's going to make more money in his cloud business than he will in his book business, if you can call it that, his retail business. He thinks the retail business is going to be dwarfed compared to his cloud business. I believe Microsoft thinks the same thing, and Google does as well. But because we put trust in these individuals, these companies, we also believe in their security. Now, how many people do you think are working at Amazon working on security? I can tell you, I don't care what company here at the table is represented, they have more security people than you do. Because that's their most important product, is not performance, it's security. Because if you don't have security, then you're not going to go to them. I am totally convinced that every media company will believe and use the cloud for their crown jewels. 3 years ago, that would have booed me off the stage. I do not believe that's true anymore. You can look at reports from Gartner and from IDC, and they all say the same thing. The public cloud is more secure than any enterprise. Even the government is using it for many, many things. I'm not sure if that's good or bad, but at any rate, that's another discussion, another can of worms. But importantly, it will be a big part of our future. And one aspect of it is artificial intelligence. Now, I'm going to look ahead 30 years. Now that you've given me the poetic license to look ahead 20, let's look ahead 30, okay, Ed, just for a few minutes? And remember Jim Phelps? Who's Jim Phelps?
Mission Impossible.
Mission Impossible. Well, he's got a new gig. In 30 years from now, he's running a media empire. And he has an assistant called Michelle. And she's actually running it for him. And let's see what Michelle, are you going to be, can I put this over here? We're going to see if we can pick this up. We're going to play this relatively short Listen to Michelle's language here and what she tells Mr. Phelps for his morning review of his network. Now, where did okay, there it is. Oops. That doesn't help me, does it?
Good morning, Mr. Phelps. Here's your October 25th, 2046 briefing. Worldwide, I am managing 450 sports channels in 85 countries. Operating margin is at 35%. There have been no visible faults in the past 425 days. Based on my forecasts, I recommend a new specialty handball channel in the Finnish language called Hand and Glove. I have access to live and historical game content for channel use. All haptic renderings and quantum transforms are prepared. ROI should be 15% within 1 year. Please note that Finland's league championships start in 65 days. This channel is ready to launch. Do you have any questions, Mr. Phelps?
Thank you, Hal.
And if Mr. Phelps does have questions, I'm sure Michelle can answer them with intelligence. This ability falls into the range that half of the experts that were interviewed by the two professors thought that machine learning would be equivalent to human abilities in terms of reasoning. Does anybody really think that at least within the next 100 years we won't have somebody like Michelle running our systems? The only thing that surprises me is they still have linear channels. But we'll see. Maybe that's wrong. We don't know what kind of channels it's going to be.
Can you blame her then if you screw up?
Can I blame her if she screws up or if I screw up?
Yeah.
She's smarter than me, I know that. So she may be my boss, as a matter of fact. Here's what Professor Alan Bartlett said. The greatest shortcomings of the human race is our inability to understand the exponential function. Just like walking 75 feet is equivalent to walking 1,000,000 miles if we think exponentially. Many of the things I discussed this evening fall into the realm of almost science fiction. If you don't what? Believe in the exponential function. Some of them, of course, will not continue forever. They have S-curves of their own. But they never seem to come to a complete dead end. Another S-curve replaces it. We can't predict all of this, but we can sense a trend that's definitely true. Now, how does this affect you as a manufacturer or an end user, especially up in Grass Valley and Sacramento? Well, it should give you a little bit of directional help. Rather than looking over here at something that is old and maybe it's making you money, we have to look over to an area that has a potential growth pattern. Even though it's just going to roll out slowly, no doubt about it. These S-curves don't show up and disappear overnight. We can pretty much bet with confidence that the exponential increase, as Niels Bohr said, will continue. Well, thank you all for your attendance, and thank you in Sacramento and Grass Valley for attending as well. Do you have any questions? Ed? I'll have to repeat them, I think, right, Keith? Yeah, I can just repeat it. The microphone, I'll just repeat. Keep it short.
One of these, another way of looking at this combination of S-curves is that when you convolve them all together, the central limit theorem would say that the convolution of all these S-curves put together is another exponential function.
That's how I'm drawing it.
Yeah.
And I give that some thought, thinking, so the question was, just because you throw an S-curve on top of another exponential function doesn't mean that it is. But if you really do look at the growth over time and how each S-curve contributes its own exponential portion to it, it kind of gives it a general constant growth, like in Moore's law, 41% a year. You can get that when you look at the other S-curves are also going at 41% a year. Even though it dies out, here comes the next one at 41% a year. It's true. It's not just a poetic diagram. Yeah, please, John.
Just a statement, and that is that you talked about the telegraph as kind of the beginning of it all,
And the facsimile, I should say, as well, in terms of imaging. Yeah.
well, I just The only argument I'd make is that's one view. There are probably a few different bases that one can start with. For me, the beginning is the photograph. So I always imagined that for me was the basis, and motion pictures started out from.
Fair enough. I guess,
So just
yeah.
different view.
Right, so John Scheick's point is that the phonograph probably is more fundamental than the photograph, sorry, the photograph, yeah. Good point. I guess the difference is I'm only talking about moving images here, and that they started with with telegraph engineers happened to discover that selenium was photoconductive. That's the only reason that I mentioned that, not that we were derived from that.
Any questions from that end? I can take them.
Any questions from the other end? Sacramento, Grass Valley? In the meantime, any other questions here? Do you think this is reasonable? Yeah. You know, and when I started on this, I was almost thinking I could embarrass myself by coming up with something so ridiculous. And you may have thought that before you came here, thinking, he can't look ahead 20 years. It's stupid. But I might be right. Just because I'm betting on the past continuing.
But you already hear people take Moore's law and apply it to storage,
Yeah.
to CPUs, and to technology in general. So what we're doing now is we're expanding that really far out and just sort of say,
I'll pass that
you
on.
can look at exponential growth in many, many areas.
Yes.
So the
So-
question
Yeah.
from the other end is, you talked about Michelle and
Right.
how can you actually tell the intelligence of a real human?
Well, I'll just use the work of, what's his name I just mentioned earlier, the guy who was at Bletchley Park. Alan Turing, thank you. I'm having a mental block on Alan. So Alan Turing, if you read his original paper, which I tried to get through when I was working on this, he actually gives the Turing test. And the way he measures intelligence is you ask a machine enough questions. He only has actually a very limited 5-minute asking period, which I think probably is a joke these days. And they can even make mistakes, and you still consider it human. But if you can't tell the difference between a machine and a human after a fixed number of questions and a fixed amount of time, then I guess you rubber stamp it as good as human. At least that's now. If you look at Watson, for example, that beat Ken Jennings and the other, what's his name, Brad, I forget the other fellow's name. He beat both of them. Now, even most scientists say that was not a Turing test. Because you couldn't ask it any question you wanted. It was only answering specific questions that popped up in a Jeopardy-like format. If you put Watson against a Turing test, it in fact hasn't passed it yet, from what I understand. It doesn't mean there's not cool things you can still do with artificial intelligence. But it's getting to that point where you won't be able to tell them apart. I hope I'm alive to see it, actually. I think it's going to be kind of exciting. Yeah, Ed, last question, yeah.
And this relates back to security. Speaking of prognosticating off in the future, in 2000, I told my CEO that within 5 to 10 years, we'd all be watching television through our ISP. And they all thought that I had rocks in my head.
But you do, Ed.
And I do.
But they're good rocks, apparently.
Yeah. But it took a little longer than 5 to 10 years. But we're there. And the rationale I have for why it took longer than what I had originally predicted is because we still, back in those days, we had the issue of protecting the content. Content owners didn't want to put their stuff out on the internet because they're afraid of losing control of it. With the advent of DRM and similar kinds of security features, that opened up the ability to go ahead and do what I had prognosticated. So security is a big issue with this. You mentioned it for a moment there in terms of cloud-based and Amazon and all these kind of stuff. But how can you elaborate more on the security aspect of all this media operating in this cloud environment, and in particular the exponential impact or that security has on this impact on this exponential growth?
So because people on the phone can't hear that, basically it's another question about security and with regard to security in the cloud. I don't want to talk about DRM because that's a distribution security aspect, and that's sort of independent of this discussion. But if you look at most people who study security in the cloud will tell you this, that it's a joint responsibility. Amazon does their part, you do your part. You can't go in there and open up all your IP ports to the outside world and not have any firewalls on your application and just say, hey, Amazon's taking care of this. Well, they're not. And when you study what needs to be done, you see there's a clear line. Here's the part that they do. Here's the part that you do. If you do it in concert with what they offer, you've got a very secure system. Very secure. But it's not just about processing and access to stored data specifically. It's a whole infrastructure of virtual private networks from your facility into the cloud, private IP addresses that nobody else shares. There's just so much going on there that it's hard to replicate on a private environment. You can do it, of course, and people do, but you can also do it in a public environment and have rock solid security. So I find it interesting that this whole security argument every year gets less and less important. And now it's flipped, it's actually turned over the other way, that your facility isn't as secure as the Amazon cloud. I think if you keep your ear tuned to this particular frequency, you will hear this more and more over the next couple of years. I'm sure we're out of time, but thank you all. Appreciate it.
Thanks, Al. And I have to, first of all, thank Cisco for hosting us tonight, and also thanks to Telestream, not only for hosting the folks in Sacramento, but also for providing us with Wirecast, which led us to do the stream. And I have to admit that I fell foul of pseudo-artificial intelligence. Now, we've all had these robocalls. Hello, this is Rachel from Cardholder Services. Right, we know that one. I got one a couple of weeks ago, and I answered the phone, not recognizing the phone number, and it was sort of silent for a minute, or not, a short period of time. And then this chirpy little girl said, oh, there you are. Sorry, I had a problem with my headset.
Yeah.
And she starts talking.
Got this one.
And then
That's a good one.
about a week later, I get the same thing. So I think, they're getting too smart now. They're trying to make it sound like a real person. But of course, it never is. Because you can't shut her up once she's going. Once she gets into the pitch, you say, stop, I don't want to do this. They'll just keep going.
But that's not artificial. That's actually a person who's intelligent who's lying.
Yes. It's a recording. It is totally but it's a smarter robocall. Anyway, thanks everybody for coming along. Bob tells me there was 25 folks up in Grass Valley joining us tonight, so a great joint meeting for all. Thanks again, Al. Thanks to Cisco and Pradeep. And
Cisco and Pradeep, yeah, thank you.
And stay tuned for more great stuff next year. And here's to the next 100 years of SMPTE.
Thank you.
And there's still some more food, so help yourself.
So I got to tell you this little known historical fact. Okay, this was between